6.2. What am I going to do? I'm going to apply Newton's laws. Okay. So what I want you to do here is that when you start to look at this thing, what we want to do here is that we want to come in and we really want to nail this type of thinking down. Okay. This is a long example, but I think it's worth it because there's a lot here. Okay. So here we go. So what we're seeing here is that Paris pushes a 13-kilogram lawnmower at constant velocity with a force of 78 newtons directed along the handle, which is at an angle of 45 degrees to the horizontal. Okay, we really got to think about that really carefully here. So the first thing, this is where maybe an identification diagram might be useful. Okay, so let's draw this guy out. So okay, so we got green grass, right? So we got our grass here, and we have a mower. So let's say that this is our mower. I mean, how does a mower look like? I have no idea. So let's say it looks like this. And then what we're seeing here is that there's a handle here. Right, there's a handle. So when I'm looking at this mower right here, what I'm really seeing here is that I'm seeing what? I'm seeing a force being applied on the handle. So when I'm thinking about what Paris is doing here, she's actually applying a force in this direction here. Now, I gotta be careful here. So I gotta be really careful with the language here. Do you really push down on a mower, or are you pushing straight on a mower? Well, it turns out that as you're applying a force on the handle of the mower, you may be pushing straight ahead, but the fact is that rod is not pushing straight ahead. That rod is pushing along the handle. That's what's connecting it. So when I say a 78 Newton force by Paris, I mean it's 78 newtons, that there's a component that is applying a force of 78 newtons in that direction right there. And then, of course, there's all these other forces that have to come into play, right? What we're assuming here is that in this case, we have, I don't think we have friction here. Do we have friction? I assume that we do. We have a retarding force. So yes, we have friction. So of course, we expect that we're going to have friction in this direction. Why is friction in that direction? Because I'm assuming that the velocity is in that direction right there. Of course, we have gravity pushing down. And of course, we have the ground pushing up, which is what we call the normal. And so that's kind of the picture that I'm thinking about. And the reason why I was really thinking about the identification forces here is because of that force of the handle. So in the beginning, she is moving at constant velocity. In other words, the acceleration is 0. So that is not my free body diagram. What is my free body diagram? I'm going to do a series of free body diagrams to show you what do I mean by a free body diagram. Okay, so what do? I take the mower, I put it as a dot. And now I start to look at these things here. So the first thing that I note, of course, is that there's the force of the handle, which I'll call F. And I know that there's mg. There's got to be some mg. And I know there's got to be some normal. And of course, there has to be some friction here. Now note, I have not scaled these forces. I'm just kind of throwing them together here. So now if I look at my coordinate system, since it's moving in this direction, that automatically tells me my positive, and I know that this angle here is 45 degrees. So there's a couple of things that I want to note here. First thing that you should note is that the angle is measured across the horizontal axis. Okay, so an important point here is angle is measured relative to horizontal axis. This implies then that any x component is then going to be a cosine of theta. Any y component is going to be a sine of theta. If the angle is measured relative to the y-axis, those guys are going to be reversed. So if you think as x as cosine, then you're pretty happy right now. So what am I seeing here? Note that I have a component. I have a component that has to go like this in the fx direction, which is f cosine, in this case, cosine 45. And then I'm going to project this guy in the y direction of fy, which should be f sine of 45. So a true free body diagram really has only vectors on the axes. So then if I continue to move in this direction here, then I'm going to scale things. So what do I know? I know that this thing is moving at constant velocity. If it's moving at constant velocity, I have what? I have balanced vectors. So that means then, if this is 3 squares in this direction for this friction here, then that means that the force in the x direction must be equal in length and equal to f cosine 45. They have to balance out. The fact that I have that this mower is staying on the ground means that it's in static equilibrium vertically. So that means that the combination of the force of gravity, let's say that the force of gravity is this big, 2 squares, and let's say that the force of the y component, f sine of 45, is 3 squares, then because this is in equilibrium, it tells me that I must have what? If this is 2 and this is 3, this must be 3 plus 2. The force of the ground, the normal, must balance those twos out. That's what I mean by scaling this thing. And then, of course, I have my x and I have my y. So now I have my free body diagram. And this is how she looks right here, right? This is a beautiful diagram. It's nice and simple and clean. So now what am I going to do? I'm going to apply Newton's second law. Let's go do it. Here I go. So now we apply N2L. And here we go. So I go the sum of the forces in the x direction. Look at my f of x. It's positive in the red. So I'm going to write f cosine 45. And then look at friction. It's in the negative direction. So I write minus friction. And then I ask the question, is this thing accelerating? And the answer is no. We said that it was moving at constant velocity. So this must be 0. And this indicates what? That this is in what? Dynamic equilibrium. And then I go to the y's. And if I go to the y's, I go the forces in the y. I see that my normal is positive. So I give it the positive sign. And then I see that the other two forces are pointed in the negative. So I got to put in my negative signs for these guys. And then, is this thing, accelerating? No. What's it in? It's in static equilibrium. So what I'm seeing here is that I now have my N2L equations. So what I do here is that I typically number them. I literally will come in and say, this is equation 1, this is equation 2, and these are my N2L equations right here. So now, what the question is asking, what is the frictional force? What is the normal force? So the goal of the question here, they say, determine friction and the normal of the surface. So what you're seeing here is that these equations here, and this is very common, is in Newton's second law here, is that we say that N2L sets up two equations and two unknowns, right? I have two equations, which I write 1 and 2, and my two unknowns, in this case, are going to be friction and the normal. So that's what I have to solve for. So here I go. So now I'm going to go write this here. So in this case, what we're seeing here is that we know what the force is. They tell us what the force is. They tell us that the mass of the mower is 13 kilograms, and the force that Paris pushes with is 78 newtons. That's what we know. Okay, so here we go. So what I'm going to do here is that I'm going to come in and I'm going to calculate the friction. So if I go calculate the friction here, what I'm going to see here is that note that friction only exists in equation 1. So if I look at this, I'm going to start with equation 1, and you could see here that this guy reads what? It reads that I have F cosine of 45 minus friction equals to 0, which then tells us clearly that this has to be F cosine of 45. And if I plug in my numbers, I get 78 newtons cosine of 45. So therefore, the frictional force in this case here has to be 55 newtons. So now I know what the frictional force is. So then I go to the second equation, because that's where the normal is at. So now I want to go in and I want to calculate the normal. So by looking at that equation, it's equation 2 that contains the normal. So then when I look at this here, you could see that it's going to be n minus mg minus f sine of 45 equals to 0. So then that tells us here that the normal must be mg plus f sine of 45. Then I'm going to start plugging in my numbers. And if I plug in my numbers, you could see here that this is going to be what? It's going to be 13 kilograms times 9.8 meters per second squared, plus the force, which is 78 newtons, times the sine of 45. And if I compute that, I get 183 newtons for the normal. So I now know what the normal is, and I now know what the frictional force is here. So what do I know right here? Well, for starters here, I'm going to go to the next piece here. Let me go bring the other piece here. So what I'm going to do here is that I now have these two. Now, one of the things that, you know what, I think I want to step back and look at this thing here, because I'm not really interpreting what is actually happening. So, and I don't want to just be in a rush to calculate things. I want to do a good job of getting you to think about intuition here. So let's go look at intuition here. And so the things that we want to look at here is we want to look at the following thing, is that when I look at Newton's second law, what is it really saying to me here? It's saying the following thing. What it does here is that question, what does this normal mean? So the first thing that I would do here is that suppose the lawnmower is stationary. If it's stationary, so that implies that there is no pushing force. And what you're seeing here is that in this scenario here, right? So if I have the mower here and there's nothing pushing this mower right here, right? It's just sitting right in here. What you're going to find here is that in this scenario here, we have what? Well, the ground is pushing up with the normal, which I'm going to call the normal's at rest. And the mass of the mower, mg, but what is the mass of the mower? Well, this is really 13 kilograms times 9.8 meters per second squared. This number is 128 newtons. So because it's at rest here, we could then say here is that it being at rest tells us here that the net force is 0. So this means then that if you're at the mower's at rest, the ground has to push up with 128 newtons here. But now compare this normal to the one where she's moving it at constant velocity. So Paris has to push downwards with a y component of Fy. So what that means here is that automatically increases the normal. Right? Because we saw here earlier that the normal was what? So this is the normal at, we should say, how about when it's being pushed at constant velocity here? This normal was mg, and now look, you could see that there's this extra term. So by her pushing down on it, it increases the normal to 183. So what you're seeing here is that the reason why there's a difference between this normal at constant velocity here is that you could see that the big difference is there's a y component in there. The ground has to push up harder, right? So we say here that the ground has to push up harder in this scenario here. And that's what I mean by interpreting what that normal means. There's a reason why this is bigger, and that's because there's a y component. Now what I want to do here is that I want to now change the scenario here and we want to go in and we want to look at B. Okay, let's go look at B here. So in this scenario here is the mower is being accelerated. Okay, the mower is now accelerating. So wait a minute. If the mower is being accelerated, we could ask the question, does Paris push harder? And the answer is yes. She absolutely has to push harder. And so if she pushes harder, what does that tell us about the normal? Well, we see that the normal, if I increase F, then F of Y increases. So this implies here is that the normal should also increase too. So picture-wise, what do we expect here? So if I go and I draw a free body diagram of both situations, it has to look something like this here. So let's say that this is Paris moving at constant velocity. So what we said here is that, let's say that mg is 2 squares, and let's say that Fy is 3 squares. And what we found here is that the normal then had to be 5 squares up like this. And then if you're moving at constant velocity, we'll say that this here is now f of x. So therefore, the friction has to be exactly the same length. So that's 1, 2, 3. Yeah, that's about the right. So in this scenario here, what we're seeing here is this is when Paris was moving at constant velocity. But look what happens. So now what we want to do here is that now she's going to accelerate. If you're going to accelerate, what should happen here? Well, for starters here, the weight of the mower should not change. But if you're going to accelerate, that means that your force in the x direction has to be bigger now. And I'm going to call this guy prime this time. So that force F prime is now larger. But wait a minute, if that's larger, then that means that the force on this guy has to be larger too. It has to be larger. So what does that do to the normal? It has to increase now. This is now the normal when you're accelerating. It should be larger here. Friction doesn't change. Friction is not speed dependent. So the free body diagrams have to look like this. So now what we want to do here is that, what do we know? Well, for starters, I now have a velocity, and check it out. I now have an acceleration. So that means there must be a net force in this direction here. Okay, so let's go write down the equations now. So if I go write down the equations, they're identical as before, right? So now I'm going to apply N2L. So if I do that, it's got to look something like this here. So I have my net force and the x direction. And what we already showed here is that this guy should be what? It's positive x prime x minus the friction. And if I just keep going along here, this should be positive f prime cosine of 45 minus the friction. But now, because it's accelerating, it should be mass times acceleration, right? That guarantees that this is occurring because we know it's speeding up. Okay, and then if I go to the y direction, everything's the same as before. So I'm going to get a positive normal. And again, I got mg and fy prime like this. So when I go in and I write this again, the big difference in this scenario here is that now, look what I'm going to do. I have my normal minus mg. Then I got to write minus f prime sine of 45. But this does not accelerate vertically. It's stationary vertically. So now we know that this is in static equilibrium. So those are my N2L equations. So since I called the other ones 1 and 2, I'm going to call this guy 3, and I'm going to call this one 4. So my N2L equations read what? They read like this here. These are my equations here. So what does the question ask for? So what you're seeing here is that the question, they ask you to determine the new force F prime and the normal. So here I go. I have two equations, 3 and 4. And now I have two unknowns, F prime and the normal. So now I use these two equations to actually calculate it. But you know what? I think I misled you here. We don't know acceleration, but we can calculate it with given information. And what they tell us here is that they tell us this here. They go in and they say that they tell you that it speeds up by 1.2 meters per second in 2 seconds. Because of this, this implies here is that the acceleration is then just the rate of change of velocity for that time. So it should be 1.2 meters per second over 2 seconds, which then gives us positive 0.6 meters per second squared. So I do know the acceleration. I know the acceleration. I know the friction from the previous example, 55 newtons. And of course, we know the mass is 13 kilograms. So what we do here is that we do have all the information. So there's only two things, right? Two things that we don't know in those equations. What do we not know? We don't know the normal. And look at that. We don't know F prime. Those are the two equations that we need to solve for those two things. So how am I going to do this here? So the way I'm going to do this is I'm going to do it the following way here. So you could see here is that I can't solve equation 4 because I don't know F prime and the normal, but equation 3 allows me to solve for F prime. So here I go. So I'm going to start with equation 3. And from this, I'm going to solve this for F prime. So look what I got to do here. Looking at equation 3, I got to take the frictional term to the other side. If I take the frictional term to the other side, I'm going to get F prime cosine of 45, and then I'm going to get MA plus friction. But now I have to isolate F prime. So if I isolate F prime, I'm going to get F prime is then going to divide it into MA plus the friction times cosine of 45. So I know what the mass is. It's 13 kilograms. We know what the acceleration is. It's 0.6 meters per second squared plus the friction of 55 divided by cosine of 45. And if you compute that, I get a number of 89 newtons for F prime. Now I have F prime. So now I could use equation 4 to get the normal. And here we go. So if I go to equation 4, what I'm going to do here is that I'm going to solve for n. So if you look at the equation up here, note I got to take F prime sine 45 to the right, and I got to take mg to the right. So if I do that, look what I'm going to get. So I'm going to get the normal. Then on this, I have mg plus F prime sine of 45. And if I do that, start to plug in my numbers, I'm going to get 13 kilograms times 9.8 meters per second squared plus the new F prime, which is 89 newtons times sine of 45. And when I compute that number, I get 190 newtons for n prime. And this is the one when you're accelerating. Now, let's see if this makes any sense here. So what we said here is that, so what we want to do here is that we want to compare the constant velocity situation versus the accelerating situation. Okay. So if I'm at constant velocity, again, acceleration equals to 0, of course. What we found here is that Paris was pushing with the force of 78 newtons. Now, when we have an acceleration of 0.6 meters per second squared, what we find here is that the force now increased. It increased to what? 89 newtons. And really, the question is, why the increase? And the reason why is that you got to look at what happened. We had Fx, right? In this case, we had Fx equal to the frictional term. But now when I look at Fx prime, it was equal to the frictional term plus the mass times the acceleration. So why is Fx prime larger? Because there's this mass times acceleration term, right? There's a mass times acceleration term here. And so that becomes important because we need that to really justify why we have that. So let's go look at the normal now. So when I looked at the normal in this case, we saw that the normal was 183 newtons. But the new normal, n prime, was equal to 190 newtons. And of course, why did it increase? Okay, it increased because the force F prime increased, right? The pushing force increased. And that really tells us exactly what we would expect here.